Our speaker is Dave McCallister. So some of you may know Dave from TAO, from the observatory where he's active with a telescope. Some of you may know he's an active amateur astronomer. He's done a lot of teaching. He really cares about teaching. Some people don't. Some people care about topics, but not teaching. But Dave really cares about the teaching as well as his topic, his area of study, which is astronomy. So he's writing his first thesis at UT. And last. But I think he'll probably, are you going to continue on for the PhD?
I think I'm going to tap out with a master's and go back into education probably.
Okay. Well, the neat thing is you may stay in this area, and you're good at astronomy. So you're just fair game for all sorts of stuff.
Easy picking, fair enough.
Okay. We're very fortunate to have you. And I think you've agreed to not only tell us about what's going on in physics and in astronomy at UT, but also some of the things you're interested in yourself. So it's been good getting to know you, and really appreciate you coming tonight.
All right, thank you so much for the invitation. This talk kind of came about. I went to the Cates Co-Star party last October and met some people from SMAS, and I hadn't gotten to interact with too many people from SMAS yet, and they just want to know what is some of the kind of astronomy related things going on at UT. Who are the professors we could go and talk to? What are some of the public talks and programs that we could go to? We just don't know. We haven't seen it before. So I said, sure, I'd love to do that. And within about a week of that happening, KO, Roger called and wanted me to do that talk for them, and then David wanted me to call and do that talk for Orion, so it filled up pretty quick. And of course the snow came, but very happy to be able to share all of the fun things we do at the University of Tennessee. I will start this talk by saying astronomy at the University of Tennessee, we actually have no astronomers at the University of Tennessee. I shouldn't say that. We have no astronomy researchers going on in our department. We don't have any observational or theoretical pure astronomy people in terms of the research programs going on, which makes the perfect place for me to go to grad school, of course. But we have a lot of astronomy in the Earth and Planetary Sciences, and our astronomy coordinator is a PhD astronomy person. So what I'm going to talk about today are the kind of astronomy related. So the astrophysics program is really strong there, and I'll talk a little bit about some of the people I'm sure that a lot of you already know, the work going on there. I went rogue with my master's thesis. It's working with a professor at another college. It's about young solar analogs, so I'll talk quite a bit about that. The education component of what we do at UT in terms of the courses that are offered, the astronomy concentration within the physics major, I'll talk about that, and the outreach. So there's a quick outline of our talk today. It's not in terms of the astrophysics there, it's not a conclusive total list, but just a few of the highlights there. Part of the thing that I'll kind of put a bee in your all's ear about, if you are looking for more people to give talks from UT, there's a requirement for a lot of the NSF grants that these professors get that they do public outreach. So there's probably a need on both sides there. So I like to start with this in terms of modeling. So a lot of the computational group, in my project is computational as well, the nature of the middle ground between experimental and theoretical physics in terms of modeling. When I was a high school teacher, I used to teach the scientific method as not a list of just you go A, B, C, D. It was really a cycle, and sometimes you could jump back and forth in between, but it was always in motion. We have physics data that informs a computer program, and we come up with a model atmosphere for the star to eventually generate a spectrum. My code that I work on outputs a spectrum that then we can compare with observational data taken on the stars that we're interested in. In terms of the work that's going on at UT, most of it's centered around stellar deaths. So what happens when stars, when they die. And I'm sure this is stuff that you would talk quite a bit about. If we have a low mass star, it kind of burps out its outer layers and the leftover core is a white dwarf. It can eat away material from its buddy and go nova, if you will, and it can actually do that recurrently. But eventually, if it gets massive enough, it won't be able to withstand that much pressure on the star, and it will have a thermonuclear supernova. When it's a large star, it's a one-trick pony. It only can do this one time. You'll have a core collapse supernova when gravity wins and crushes the star all the way past the electron degeneracy point. Okay. Computational models provide insight, and it's kind of a middle ground between experimental and theoretical folks. And we do have one of the finest astrophysics, computational astrophysics programs in the world here. This is a big group. I only have two of our people up here. We've got Rafe Hicks, Tony Mezzacappa. There's a whole host of these people over at Oak Ridge that work on the Titan supercomputer with the Chimera code. And I'm pretty sure that this is the only code that has all of these four things together, all in one simulation, and it's multi-dimensional. I have a video. It's a bit old, and Dr. Mezzacappa is going to come on and talk to us, and then I'll show a 3D video of one of their explosions.
How do massive stars 10 times the mass of our Sun die in spectacular stellar explosions known as core collapse supernovae? This is one of the key questions being addressed by the Terascale Supernova Initiative, funded by DOE's Office of Science, in particular by their SIDAC program. Why is this question being addressed? Core collapse supernovae are the dominant source of elements in the universe, without which life as we know it would not exist. Therefore, understanding how they occur is tantamount to understanding how we came to be in the universe, and consequently, one of the most important unsolved problems in astrophysics. Core collapse supernovae are complex, turbulent, three-dimensional events that will require multi-physics, multi-scale, three-dimensional simulations. These events probe extremes of nature that, relative to our everyday world, are simply unfathomable. Take, for example, the dense matter in the neutron star produced by the supernova, one of the supernova's remnants. 1 cubic centimeter, the size of a single sugar cube, would weigh as much as the entire human race. And the challenges don't stop there. Three-dimensional core collapse supernova simulations will produce data at the staggering rate of hundreds of terabytes per simulation. For scientific discovery, these data will have to be analyzed and visualized by scientists across the United States. The infrastructure that must be in place to accomplish this, namely the infrastructure for data management, networking, visualization, and enabling the overall scientific process or workflow, is daunting. Daunting, but not impossible. Through the SIDAC program, multidisciplinary teams of scientists, mathematicians, and computer scientists have been assembled to tackle these scientific and infrastructure problems, and with great success.
If you noticed a little bit of the sloshing back and forth motion in the video, it's called a standing accretion shock instability, and this group was one of the pioneers in terms of identifying this. And you can tell these stars don't collapse spherically symmetrically, so you need multiple dimensions in order to characterize it fully. But it's very computationally expensive, hence the supercomputer. Another person that kind of bridges over into the nuclear side as well is Dr. Steiner. And he works with neutron stars to understand how nuclear physics works. That's kind of his laboratory, is neutron stars. And how the nuclear physics does play a role in these types of objects. I attended a talk by him one time, and the topic was something around the fastest sound in the universe, and it was sound waves on the crust of a neutron star. The matter's so dense that the sound waves move very quickly. On the experimental side, among other people, we have Dr. Kate Jones. She kind of does the opposite. She uses the nuclear reactions with the reactors at Oak Ridge to understand more about the atomic nucleus and how the nuclear process happened during supernova. So the R process, the rapid neutron capture process, is responsible for about half of the periodic table. And so she works a little bit on the experimental side. And she works in neutron poor nuclei. So this is a chart with number of protons along the horizontal axis, number of neutrons on the vertical axis. So all of these little squares are isotopes. So these are elements of a particular number of protons and neutrons. And so she works along the bottom part of this. And then 10, doubly magic 10, is right there as well. She works on those. Understanding how this table gets filled out. Okay. This is Dr. Sean Lindsay. He is the astronomy coordinator. He's not a research faculty. He's in charge of our astronomy education programs, but he does actually work in the Earth and Planetary Sciences on learning how the solar system got cooked initially. Right? So how do we get all of the things on the right to condense down out of clouds such as the one on the left, with all the diversity of things that we have in our solar system. So he looks at comet dust grains, primitive asteroids, radiative transfer, which has come in handy for my project that I'm working on. Okay, and that brings us to me. I'll tell you how I came into this project at the end of this little segment right here, but the Young Solar Analogs project has been going on for about 10 years now. There's a professor at Appalachian State, Dr. Richard Gray, and a professor at Marshall University, Dr. John Sakin, as well as an astronomer with the Vatican Observatory, that have been working on characterizing young stars like the sun. They're trying to get an idea of what the sun was like when it was not necessarily a baby or even a adolescent, like a preteen type. So if you've ever spent a whole lot of time with preteens and young teenagers, they can be sometimes a little violent, and they're covered in spots, just like our stars. They got a lot of spots, put out a lot of radiation, a lot of hectic, cause havoc in the area around them. So the age range we're looking at, we've got 30 program stars between 300 million and 1.5 billion years old in a spectral range class, about a class to a class and a half on either side of the where the sun is. So it's, again, giving us a window to what the sun was like in the early days of our solar system. And interestingly, all of these stars put out about 100 times more flux in far ultraviolet and X-ray, which would not be conducive to life now. If our sun was doing that now, it'd be a very, very bad place to live. So it's an interesting question. So there are program stars in the sun there for a comparison. They are relatively bright. I think the dimmest one is a apparent magnitude of 6.6. They have relatively low solar-like metallicities and surface gravities, and the effective temperature range between about 5,000 Kelvin to 6,200 Kelvin. And little solar dermatology for you. On the outside, the two layers that we're most interested in are the photosphere, which is the part of the sun that you mostly see, right? We put a white light filter to kill the bulk of the light that comes in to view sunspots. But then there's another layer on top of that, a thin layer called the chromosphere. And if you've ever looked through an H-alpha scope, that's what you're looking at, is the chromosphere. So my project looks at the interactions between these two. We're trying to characterize the magnetic activity of the star. And what happens when a star is more magnetically active, just like our sun? It has more spots. It has more storms, magnetic storms on the sun, on the surface. And what causes the stellar activity, if you will, all of this extra flux, is going to be the magnetic field, the dynamics of the magnetic field. So we're going to get a lot more, about 100 times more, far ultraviolet, extreme ultraviolet, and X-ray emissions, and we also have much more active regions. The observations that have taken place over the 10 years that the project has been collecting data have been spectroscopic observations. I'll show you the two instruments that they're using in a moment, but they're looking for emissions in particular band passes for the calcium 2H and K lines, G band calcium 1 and H gamma lines, but we're also doing photometric observations, and that's mostly what my project is looking at, the photometric component of this. Now these wavelengths that are listed there, it's not a single bandpass. There is a width to them that I'll discuss in a moment as well. Some of our program stars do some weird things with their photometry that I'll get into in a moment. So we were talking about this in the board meeting before we started about the spectrum, the electromagnetic spectrum, everything from radio waves to gamma rays, and there's only a very thin window of that we can actually see. It has to do with what the atmosphere lets in. This is a chart of the atmospheric transmittance for electromagnetic waves. We're interested in gamma rays, X-rays, and ultraviolet light, and we can't get that from the ground. Okay, unless we want to steal the keys to a space telescope to look at our 30 stars over and over, we're not going to be able to get that. So what we have are some very easily measured proxies. The proxies that we use help us characterize these X-ray fluxes without actually having to see the X-rays. So we don't need an X-ray telescope. If you're familiar with photometry at all, the Johnson-Cousins systems were looking for specific amounts of radiation in these bands, particularly the first three, U, B, and V, which stand for ultraviolet, blue, and visible. And for whatever reason, this particular person didn't choose colors that make sense for the band passes. So blue is green and ultraviolet is red. But those are the bands that we're looking at. And if you compare the fluxes in those two in any two bands, you can characterize the temperature of the star. So for instance, if we looked at the flux in the blue filter for a 20K star compared to a 3K star, it's going to have a lot more blue than red in the 20K star, but it's actually going to have more red than blue in the 3K. So that's part of how photometric systems work, is that you can compare the two of them to characterize the temperature of the star. Another thing that they did in this project that was really neat, and I've never heard of anyone doing this before, typically when you're studying the photometry, you are comparing your variable star to some standard known star, right? So, all of the things that can mess up the photometry, such as the air mass, the height that the star is in the sky if it's close to the meridian. You want to be able to compare your star to something that's close to it. And our problem is, in one frame, our program stars are by several magnitudes brighter than all the other stars around, so we don't have a good comparison. So they did something really neat. They've taken so many nights of observations, they have a dedicated set of scopes for this, that they've actually added up the flux from the other stars in the field to make a superstar. And that's their basis for comparison, is all the other stars there. And with that, they've gotten millimag photometric error, which for this type of a program was fantastic. They actually also, interestingly, defocus to spread the photons over a wider number of pixels to, again, try to add up more of the flux from those other stars in the field. We use proxies. We look at those, the spectroscopy in the H and K lines, so it's doubly ionized calcium ions. And those are very strong correlators with X-ray flux and far ultraviolet excesses. And you can use space telescopes to correlate those as well. Calcium 2H and K actually has quite a long history in terms of the program stars that have been used in the past. So this particular way of characterizing a star's stellar activity has quite a bit of history. We have something called the Mount Wilson X index, and that is something I'll explain on the next slide. It characterizes the height of the activity in the chromosphere of a star, and we're again correlating that with the magnetic activity of the entire star, which is the chromosphere. This particular program, for goodness, 40 some years there, monitored 100 stars that are around the same F, G, and K stellar type stars that we're looking at. They were looking for, do stars have an activity cycle like our sun's 11-year cycle? A lot of them did. Some did not have any cycle that they could tell. It was too sporadic, and some really didn't vary that much at all. So our program kind of focuses on the younger end of those stars. This is a spectrum. We have normalized flux on the vertical, and we have wavelength on the horizontal. And H and K are two lines, again caused by absorption and re-emission of doubly ionized calcium. And you see in the bottom of these dips right here, there's a little bump. And what the Mount Wilson S index measures is actually the height of that bump compared to the overall depth of the well. So that's what they're looking at in terms of the stellar activity. The higher that bump relative to the depth, the more active the chromosphere of the star is. And again, there's about 40 some years of data that kind of correlate with this particular index. They have two telescopes that they've used so far. One is a dedicated scope for Appalachian State, the Dark Sky Observatory. They have a 32-inch Ritchie that they use for spectroscopy, and only a 6-inch astrograph. Again, our program stars are bright. We don't need big, elaborate equipment to monitor these relatively bright stars. For long-term changes in it, we don't need a big telescope. However, when you're looking at courses over the course of an evening, changes in the star, we do need a little bit more flux for that. So the VAT scope on Mount Graham, I always like this picture. It's an F1. If you're familiar with telescopes, it's like a big, almost a snuff can. Yeah, it's as wide as it is long. So they have a 6-foot wide F1 Ritchie for that, and then just a 6-inch f3.5 camera lens for their photometry. Both the photometric scopes are robotic, so they have their pre-programmed every night as they check for the stars to be clear, and then they take their programmed stars every night as they pass the local meridian. So what motivated my addition to this was there were some stars that were chromospherically active. The S-index overnights were just going up and down and scattering all over the place, and yet the star was maintaining a very similar amount of photometric flux. So the B and the V bands were stable. And you would think that if the star is very active, you're going to have a lot of spots. Especially in these young stars, you get some rather large spots that can cause the photometry to go down, but the magnetic activity to go up. So what I'm trying to model is a star that is photometrically stable but has a lot of spots on it. Okay. It builds on a program that my advisor, Dr. Gray, used. We have a program that can create a spectrum for a star. It's called Spectrum. We're not real inventive when it comes to naming things in astronomy. The Ring Nebula, right? The 30-meter telescope. We just like to keep it simple. The program that Dr. Gray has would treat the star kind of like a Minecraft or a Lego block. It would just be this big blob. It had some optical depth to it, and it would tell you, it would analyze about 310 different isotopes to figure out what the spectrum would look like. But geometrically, I can't introduce a spot to a blob, right? So what I have done is to make a whole bunch of blobs. This is my model star. It's a 10 by 10 grid. Eventually, we'll move up to a 100 by 100 grid. And we have a plage around the outside, and we have a penumbra of a lower temperature, and then the spot, the umbra, right in the middle at a darker temperature. So at a lower temperature, and then it's a darker spot. And then we're going to rotate this spot across the face of the star and take the photometry every time, just like the telescope would. And by the way, we're wrapping that grid, latitude and longitude, around the disk and deflecting it accordingly. So it worked. Finally, I had a bug in the code that instead of resetting the flux every rotation, it would just keep adding up, and it would just go up by the same amount every time. This was my first plot where I knew the code had actually worked. When the spot started just off center, moved right into the center, and then rotated off. And there's a little bit of up and down right here where the plage was all that was left on the edge of the star. So the next steps for that particular, my part of the code, is that I need to add in differential rotation. So depending on the latitude, the spot's going to move at different speeds, have spots that appear and disappear. We're going to have active latitudes where you have two spots about 180 degrees apart. We have the magnetic field lines of the star coming out in one spot, coming in another. And having that, you could very easily explain why the star doesn't change a whole lot if one spot's moving off right as another spot's moving on. We also need to incorporate, these stars have an inclination, so they're not all just rotating with the edge on with the equator. So we've got to be able to incline the star towards us or away from us and have the spot rotate in the correct fashion. Also, we got to use a lot higher resolution. So how the future papers for the Young Solar Analogs project, the first paper that they did in 2015 was long-term. It released all of the data they had collected in terms of the stellar cycles, like the sun's 22-year cycles. The next one will be medium. That's where my project in, kind of the days to months as the spots rotate across these stars. And short in terms of hours to minutes. That's why we need the VAT scope. And they think they may have caught a white light flare in one of the program stars on the VAT scope. And also, there's a second robotic observatory plan dedicated to this project, consisting of a 28-inch Dob, motorized from the base as the spectroscope. And they're actually using the spectrometer as part of the counterweight in the back, which is kind of a neat design. Located outside of Genoa, West Virginia. Why there? That is where my family's farm is. So one day, out of nowhere, Dr. Sakin from Marshall called me and said, "What's the status of the Joseph Dale Perry Memorial Observatory?" So I see it's got a clear sky clock, and there's a website there. I just wanted to know what the status of the project is. And I said, well, my grandfather passed away, and he was the one that got me interested in astronomy. And I said, one day I'm going to build an observatory on his farm. But all I had done was register the site. I said, all I've got is a site. He's like, well, I've got everything except a site. I've got a telescope, money for a building. I just need a place to put it. And I said, well, I think we've got everything we need done. So that was a bit of serendipity. Okay, so moving on from the heavy research side, what do we do at UT in terms of astronomy offerings? The first 4 classes there are part of our general education sequence. We have the 151, 152 classes that are lectures, and then the 153 and 154 that are labs. I'm teaching 2 sections of 153. And students are expected to do 1 full sequence of that, or geology or some other 100-level course as part of their general studies. Students that are more interested in the higher level stuff will take the 217, 218, and I was a TA for that last year actually for both those courses. I've sat in on 411 and 421, both taught by Dr. Guidry, fantastic. He's actually using his own textbook for both of those, but that starts to get more into the nitty-gritty of things. Students that graduate with a specialization, a concentration in astronomy, will do a special topic course, and then we have a graduate course as well. And I'll also put this on here. Many of you know Paul Lewis, who's our primary outreach person in terms of astronomy. He teaches a not-for-credit Exploring the Night Sky, where he uses our facilities and our equipment in a non-credit setting. So we don't have an astronomy major, and we don't really even have an astronomy minor. We have a physics major with an astronomy concentration. They have to take one of the 3 introductory courses that are in this box, and all of these courses, and then all of these courses as part of the core that they take. Typically, if you want to go into graduate school in astronomy, you're expected to have an extremely strong background in physics. So much so that many places ask you to take the physics GRE before you get in. Okay, so in terms of the equipment, we have on the rooftop observing deck, we have 8 8-inch LX200s, very popular model from Meade on Losmandy GM8s. The GM8s were new as of this summer. I was part of the effort to take them off their fork mounts and put dovetails on them and put them on these equatorial mounts. We still have one LX200 on its fork mount. We have a 10-inch Meade on a G11 and an 11-inch Celestron on a G11. We have a 7-inch Max-Sudolph cassegrain, which I think is the best scope on the roof. Fantastic planetary views. And then for solar observing, we have a couple of white light filters we can place over the scopes that we have there, but also the Lunt double stack H-alpha scope, which came in very handy for the eclipse season. We had a term, I went to a couple conferences where we talked about outreach and things. We eventually coined a term called eclipse fatigue. So people had been working on this for so long, they were just ready for it to get over with. So we'll talk a little bit about the eclipse and what we did later on. That was the original format for our LX200s. They were polar mounted on fork arms. Has anybody ever polar aligned a fork arm like this? It's tough, isn't it? It's hard to make sure that the optical tube and the forks are parallel to each other before you go trying to find Polaris in it. I've finally figured out a way to install a camera and then spin it in right ascension. I just looked for the way that the stars were turning. If all the stars were doing this, I knew I had to move it over there. And around the time that I'd really perfected that technique, we replaced them all, of course. But the problem was if a butterfly sneezed 5 miles away, it would go out of alignment for whatever reason. So we had a couple problems with the fork mounts. As you can see, in the background there, we put very heavy bags over the telescopes. They won't let us put a dome or any type of a roll-off roof up there, so we have to keep them up there. The hand controllers did not weather that well. We had to replace a lot of hand controllers. We really didn't lose any scopes in terms of the weathering up there, except for the hang trawlers. Meade started to get a little bit crabby with working with us on terms of replacing some of the parts. They wanted us to buy new scopes, and we really didn't want to buy new scopes. So we replaced them, and it took about 20 seconds per fork mount. More like 20 minutes. And I ended up getting, I think the fastest was about 19 minutes. This was toward the end. I videotaped myself doing it. There is a problem with their design for the 8-inch. We recently deforked a 12-inch at TAO. And I was asked to help because of this actual video, because they'd known that I'd done something similar. The bolts that I'm taking off right there at the end are hidden behind the fork arms, so you have to completely disassemble the scope, the fork arms, to get to them. 10-inch, 11-inch, anything bigger than that, no problem, you can get to it. But for this particular one, I found one website that told that somebody had to do it, and this person actually used a blowtorch to melt the super glue in it. So it was a bit of a procedure. I was able to break loose our super glue because it had been on the roof for so long. So there's a view from the roof of two of our primary light polluters downtown. One is on the right is Ayers Hall, one of the more photogenic places on campus, so they keep it lit up 24 hours a day. And then on the left you can see to our south there's some sort of athletic facility. And it's the Nealon Nebula when it gets lit up. And luckily this past fall, not a single night we were up there. And we were up there a lot. We had great weather. No interference from the Nealon. I don't know if they just gave up early in the season and just stopped going onto the field at night when they started doing so bad. But we had no problems with the night sky, with the football lights. The picture on the left is actually, I helped Paul rescue a 10-inch that had been just kind of collecting dust downstairs. We had a G11 we weren't using, so we got a home for it in the middle of the student side of the roof. But I show this picture because the football lights are on in this picture. He used a flash for this picture, but you can see how much light is on the buildings behind me there. The picture on the right is of us on a typical night without the lights on. And even without the lights on, there's still quite a bit of light that makes its way onto the roof, let alone up and back down through light pollution. And if you've been on campus, there is a design of street lamp fixture that's essentially like that. It's completely open all the way around. There's no cutoff at all on these. So we're hoping that eventually they will replace those with something a little bit smarter. I know that Knox County in general is doing an LED replacement. So we're hoping that they pick the right temperature. But of course, we're good sports, so we use them to test out our solar eclipse glasses. And sure enough, you could actually see the lights through our solar eclipse glasses. I'll get more into the eclipse at the end there when we talk about our outreach. We have, for every telescope on the student end, a Santa Barbara ST402 camera. It takes quite a bit of patience, but you can eventually get some good pictures there. It's not anything earth-shattering in terms of the resolution, and from the roof, there's some stability issues. If somebody walks on the other end of the roof, it jiggles a little bit. It's hard to focus. It requires some work, but eventually you can bring down. You know, if you're not into this and see all these great pictures that George and other people put up, you might think, hey, that's a fantastic picture. It's really not. The stars are a little bloated. But for students that go up on the roof as part of their astronomy lab experience, this is the coolest thing that they've ever seen. And frequently they come in at 8 o'clock at night and they don't want to be there. It's kind of, I'd rather be somewhere else. And by the time they leave, it's like, that's pretty cool. This is a pretty neat thing that they did. It's one of those things you like as a teacher when they kind of connect with something. Apparently, this is a well-kept secret. We have a planetarium at UT. We had a KO meeting there in November. Paul and Dr. Larry Taylor, who was recently passed away, he was the chair of the Earth and Planetary Sciences department, helped bring this to campus, and we use it quite a bit. Our lab students use it as part of the lab program. We have field trips that come in. I help out a little bit with that, but that's mostly Paul. It is a digital planetarium. It's not the old ball and light bulb with the holes sticking on it. It's not optical mechanical. It's all digital. It's not a super high def, but it's good for what we use it for. It has a lot of utility and a lot of stuff we haven't actually tapped yet, including the upgraded operating system that allows us to actually fly through the Milky Way. It's 30 seats, typical one classroom size. The programs are usually around an hour. We really hit the outreach part hard. This is a picture of me from a video I'm going to show you here in a minute, where we ran through simulations of the day of the eclipse to help people kind of get an idea of what they were going to see if they were in the path. Another day at the office there, so kind of a neat picture. We can put up those constellation lines, and in different cultures as well. The Polynesian one was one that's been very recently popular because of Maui's fishhook. If you've seen Moana, the animated movie, the kids all like Maui's fishhook. In terms of education and public outreach, I help out when I can, but this is mostly Paul, what he does. They do extra credit sessions for the lecture students. I have been more or less in charge of the telescope labs on the student end of the roof. I'm handing that off to the folks that will take over after I'm gone, so they're kind of taking the lead on that. We have open houses on the roof every first and third Friday, and that should be easy for this group because it's the day before Orion meets, unless something weird happens with the month ending on a Friday. There is a recently formed UT Astronomy Club, which I think is actually the beginning of where SMAS started. SMAS started as the UT Astronomy Club. When everybody graduated, they formed SMAS. There's about 80 people, 80 students on the email list. They are doing a great job utilizing the equipment that we have here, but they're also putting together a Scout Badge College for Boy Scouts to come in. And with the astronomy badge, they need to come to a planetarium as part of their study there. So helping them along the way as well. Planetarium shows for elementary schools, the way that our lab schedule works, we can only do that on Fridays for most of the year. And so that backs up fairly quickly. But anybody that wants to try to do this for their children should contact Paul at the department. We'd have public programs. Every so often we'll announce what's going on. We had a group that wanted to contact the ISS with amateur radio a while back, and they had a meeting from UT. They had problems with it, and they ended up having to reschedule. There's a Physics for Everyone Saturday lecture series. All of them are interesting. Not all of them are astronomy related. The next one is, and I'll give you that information at the end. And of course, the eclipse outreach. That was the first and last for everybody for the last several years. This is a look on the roof. This was one of our solar Sundays we did over the summer. We gave away 10,000 eclipse glasses in total. Actually, the last little bit of eclipse glasses I gave away to a meeting at TAO the Saturday before the eclipse. We had the last 50. I said, please just don't sell them. Use them. Don't sell them, since we gave them to you. We had quite a few people come through. We also helped Knox County Schools get their glasses as well. This is another look at Paul's end of the roof from the student end of the roof. I helped make our department in total helped make a video getting people more information about the eclipse. I'm going to show you a clip from that right here. You just see Paul, myself, and Dr. Lindsay.
Looking at the sunspot.
Okay, what do you see?
Oh, it's right there! Wow.
In anticipation of the eclipse coming to the area, we are doing some outreach programs here where we have solar observations on the roof. We can safely view the sun and different wavelengths to get different perspectives, and also running through simulations of the day of the eclipse here in the planetarium.
What we're trying to do here more than anything else is educate the public. Let people understand how important it is that we do it safely. I'm holding a pair of solar eclipse glasses. Now, we've had sunglasses all our lives, and I can tell you for certain sunglasses are not for looking at the sun. These have a neutral density factor that only allows 1/100,000th of the ambient light, the sunlight, to pass through. That's safe to look at the sun with. Anything less than that is not safe. So if you have a certified pair of solar glasses, then you've got the right thing.
When the moon is blocking the sun, totality occurs. You actually take off your solar filter. That's when you can see the corona, the atmosphere around the sun, and you can take in the full spectacle that is the eclipse.
I truly believe it's a life-changing experience that everybody should make an effort to do and go see a total solar eclipse.
We tried. We really, really tried to get the word out about getting into the path of totality. So there was more to this video, and Dr. Littman was on right there at the very tail end. Dr. Littman is in the journalism department, has written several fantastic books about the eclipse. Despite our pleading, the administration still had a party on campus for the students. They had 8,000 eclipse glasses, and they had all of them given away, so they had at least 8,000 students on Ayers lawn, and they got to see a fantastic partial eclipse. It's 99%. But we pleaded with them to figure out a way to get them into the 5 miles south that they needed to go down Alcoa. Said, take an Uber, just do something. These are the glasses we gave away, and we checked. They were definitely certified, because that was an issue there getting down towards the end. They became scarce, and people wanting a lot of money. Having done my bit for King and Country, I stayed at my house. I was afraid it was going to be crowded with the roads, and I had people from my neighbors come over. I had about 40 people come over at some point to look at the partial phases. This is the entirely wrong equipment to try to photograph an eclipse. The focal lengths are too high, so I can only see bits at a time. I live streamed on Facebook through the motorized Dobsonian. It's a 16-inch, and then I had a 14-inch. An old orange tube C14. It is a film filter. I'm a grad student. I don't have that kind of money. I have a little bit of money. I got some stuff. This was all the Dob. I saved my pennies on and got that new. But the orange tube and the Titan mount I got on Astromart for about a third of what I would have paid. That kind of stuff brand new. So there are deals to be had. There's also the old Coronado PST. That's the only scope I borrowed from school at that point. And I told myself if anything were to go wrong, technically I was just going to stop and watch. And nothing did, and we were able to get a couple of good pictures. This one made it to the news, so I got to cheerlead on our physics department on the news a little bit. We also have a memorandum of understanding with Pickett State Park up above Jamestown, about 2 hours away. They are building a astronomy-only campground where there's red light rules. You can't have any campfires. They're going to have a bathhouse and everything for you up there, and 8x8 square concrete pads to put your equipment, all the electricity and everything you need. The site itself is actually gorgeous. It was a recent, not as recently as another park, but about 2 years ago, they received their dark sky certification, a silver tier. This is the ridge. It actually looks over into Pogue Creek Canyon. It's a really, really pretty area, but they're going to clear that off. They're going to plant some vegetation that is height limited. It won't grow to the heights that would block out telescopes. They are going to build an observatory there as well, with the understanding that we're going to help them with their public program. So that's part of the MOU that we signed with them. That all happened very quickly and then ground to a halt. I think we're still on the list in terms of those things getting done, but I haven't heard much from that front for about a year. This is the Build the Comet. If you've seen Paul do this is one of the Paul Lewis classics. He takes dry ice, dirt and rock, kind of a silicate material. The rubber ducky there is honey, so that's the organic material. Sometimes it's found in comets. And he has the children, there's a table full of kids right there that are helping them kind of crush it up, and then you kind of look and see what the comet is. It's a big dirty snowball. So it helps them kind of figure out how to build a comet. This was at a Pickett event as well. Okay, all right. So that's kind of not so much in a nutshell, but a broad picture of the astronomy-related things that the department supports. We do have a couple of upcoming public events. January. Wait a minute. That's wrong. It'll be next week. This is not the. It's the first and third Fridays. I changed that from last week. This is the snow's fault. This would have been right if the snow hadn't got us next week. So it'll be, I guess it's the second. It'll be the first Friday in February, starting at 8:30 p.m. It's open to everyone. You're kind of on your own with parking. That's kind of the only thing about it. There's a garage on White Avenue where most people park. Some people kind of risk it and just park around the hill. Some people get away with it. Some people don't. Kind of up to you. The Saturday morning stuff, though, you are allowed to park in the 11th Street garage for free. And the next Saturday morning physics is Dr. Mizakappa, who was in one of our videos earlier, on the cosmic circle of life, death of massive stars and the origin of elements. And that is going to be a fantastic talk.
What time does that one start?
I'd have to check. It's in the morning. I want to say 11 a.m. They also live stream it on their Facebook page, on the department Facebook page. I'm pretty sure it's 11 a.m. Okay. Paul will be going. I'm going to be in thesis writing mode for the rest of the spring, so I'm going to be on lockdown. I'm not going to be allowed to go play until I get my work done. So Paul will be going to these events as part of the department's outreach. Wilderness State Road, Park of Virginia in March. Fall Creek Falls, I believe they are closing that in soon. I think this might be the last Fall Creek Falls, Tennessee Spring Star Party for a couple of years as they renovate that. So I will try my best to be there for that because I do want to see that. I've not been there before. And then Paul also throughout the year has events at Big South Fork, and the next one is in May. Okay. And with that, I thank you so much for your attention and for allowing me to be here today. Thank you. Happy to take any questions. Yes, sir.
What are you doing there at UT with infrared photography?
Infrared photography, the photography that we do in terms of our education program is all in the visible spectrum. We don't do any infrared. That is, in terms of our equipment officially we have. We might have some people trying it on their own, but the cameras that we use have RGB. It's not the same as the Johnson Cousins filters. To get our color grabs, they're monochromatic. So that's the only thing in terms of color photography that we have.
You can just see a lot. I've
Yeah.
taken night vision stuff.
Well, we have some fantastic equipment, and we have it on the worst place in East Tennessee to have it, right? So it's kind of a balancing act into how much. There's some other stuff that we want to do. I would like to have a demo up there of what spectroscopy is. We have a very low-cost spectroscopy unit from Vernier who makes educational lab type stuff. And we want to mount a fiber optic cable into an eyepiece to feed into our spectrometer so they can see what it looks like. And I'd also like to have a photometry rig as well to kind of just show them what the concept is in terms of what astronomers really do in terms of experimental stuff. But we didn't have any plans to do infrared that I know of.
How many remote labs does UT have?
Remote labs?
Remote observatories.
Remote observatories. We don't have any ourselves, right? We're hoping that Pickett, we can do something robotic there, would be our first one. Again, there's no research, there's no money for research there because there's no research professors there to do it. Everything we do is outreach. So
back to your grandfather's property in West Virginia.
Yes.
So you're having an observatory built on your grandfather's property?
Yes. I was going to, and I actually just bought a sky shed pod to house that orange scope, and I tried it in the TAO TAO observatory when we'd taken down the 11-inch. It's a tight fit. It's a lot tighter fit than I thought it was going to be, so I'm going to need the zenith table to push it off. So I was at least going to have that, but they want to also have, essentially, it's a 28-inch Dob in a roll-off roof coffin, essentially. It's really, really, they're going to store it straight down, roll it off. They're only really going to take pictures of and take data when the stars are close to the meridian. So it doesn't need a lot of, it's about 10 feet high. Yeah, it's a big scope. So it really only goes north and south, and a little bit left and right, east and west, but it's going to be taking data when things are at their lowest air mass near the meridian. So, well, thank you guys so much. I appreciate it, and hopefully learn a little bit of what we're doing at UT and inform the groups if they want to ask some of the professors and some of the other folks here to do some talk. The facilities there, in terms of the classrooms, the educational opportunities at TAO for outreach. I was a high school teacher, so I taught physics, and not everybody's cup of tea physics, right? And you have some students that get excited, but a lot of times it's kind of a struggle. But occasionally you do a lesson and somebody would just go, "Whoa, that's really cool!" And it connects, and it's one of the best feelings you can have as a teacher. And what I like about astronomy is that person after person after person will come to your scope and look at Saturn and do that exact same thing. Wow, that's amazing. And one of my favorite quotes is, astronomy is the gateway drug to an addiction to science. Right? It is, yeah. All right, thank you all so much.